Hi, and welcome to Lecture 3 of Week 4 for the Quantum Universe for Educators. In this lecture, we're going to get stuck into Niels Bohr's model of the atom and how it solved the stability issues with Rutherford's model of the atom. So, to remind ourselves, in 1909, Rutherford, Geiger, and Marsden conducted their famous gold foil experiment, which showed experimentally that atoms have this structure in which the positive charge is concentrated entirely in a small region of space that we call the nucleus, and the electrons are moving around the nucleus. But Maxwell's electrodynamics predicts that any charge moving in a circle is going to radiate electromagnetic waves and therefore lose energy and spiral in. So Bohr in 1913 proposed the following solution, and the solution is in the spirit of the solutions that Planck and Einstein came up when they were dealing with the issue of trying to describe the black body spectrum or the photoelectric effect. It's the kind of solution that says, okay, well, let's invent a new principle of physics that says that the thing that we thought couldn't happen can actually happen, and then see how far that gets us. Now, of course, you have to do it in a clever and sophisticated way in order to make it work, and in order for it to have a chance of somewhere down the road finding a physical theory that is coherent and works with what we already know. So Bohr came up with the following two new physical principles, and I've pulled out these quotes from his paper directly. The first principle is that the dynamical equilibrium of the systems in the stationary states can be discussed by help of the ordinary mechanics, while the passing of the systems between different stationary states cannot be treated on that basis. So let me explain what he's saying here. When he refers to stationary states, what he's referring to are the orbits of the electrons. So in chemistry class, we often have this cartoon picture of an atom where the electrons are moving in circular orbits. So we'll go with this for now, even though later on we'll find that's not really an accurate picture of what is going on inside of atoms. But it's a useful heuristic, if you will. So the stationary state is a circular orbit of an electron. And what he's saying here is that we can describe these stationary states just using Newtonian mechanics. So we can describe the electron orbits using Newtonian mechanics. So he's saying that we could treat the electrons kind of like the moon orbiting the Earth, all right, which we can describe using just F equals ma, Newton's second law, and an inverse square law for the force between the moon and the Earth. In the case of the moon and the Earth, the inverse square law comes from the force of gravity. For the electron and the nucleus, it is the Coulomb law for the electrostatic force. But importantly, he is asserting that we don't need to worry about the electron radiating away its energy. He's essentially saying, look, experiments tell us that this is how the atom is arranged. We observe that atoms are stable. Matter is not collapsing in on itself all around us. Therefore, Maxwell's electromagnetism doesn't work in the atom. That these electrons do not radiate away their energy, even though they are moving in a circle. They are constantly accelerating in a circular motion. So he's saying that let's treat the electrons as moving in orbits, as described by Newtonian mechanics. But when we want to describe how an electron moves from one orbit to another orbit, then we have to find some other theory, some other description. Newtonian mechanics doesn't describe how electrons move between orbits. It only describes how they move within a single orbit. The second principle he comes up with is that the latter, the change between stationary states, the change of an electron between two orbits, is followed by the emission of a homogeneous radiation for which the relation between the frequency and the amount of energy emitted is the one given by Planck's theory. So what he's saying here is that if an electron jumps from a higher orbit to a lower orbit, it emits homogeneous radiation, and by homogeneous he means electromagnetic radiation at a single frequency, not with a range of frequencies, a single frequency or wavelength. And that frequency is given by Planck's formula, right, that he came up with to describe black body radiation, and that Einstein generalized to say was the the formula that tells us the energy of a photon of light. Okay, and in Bohr's 1913 formulation of his model, in his picture, each electron occupies its own orbit, its own energy level. Okay, so we can begin to put together a cartoon picture of what's going on in the atom. We have electrons that are following certain orbits, and only certain orbits are allowed. Right? There are a whole range of orbits that are not allowed, and only certain orbits that are allowed, that are stable, and that electrons gain and lose energy by jumping between the allowed orbits of the atom, and that when they do jump between orbits, they either emit or absorb light of a certain frequency, and that frequency is given by Planck's formula, where the energy of the light absorbed or emitted is equal to the difference in energy between the electron in the higher orbit and the electron in the lower orbit. So it's worth noting that this first principle that Bohr comes up with breaks the rule that accelerating charges radiate away their energy as electromagnetic radiation. And the second principle breaks the rule that nothing happens instantaneously, because it's saying that the electrons jump between their orbits instantaneously. And it also breaks the rule that charge, when moving between different orbits, should spiral between them, emitting radiation over a range of frequencies. So there are a couple of ways that it's breaking the rules of classical physics, but it is saying that whilst an electron is in a particular orbit, or its stationary state as Bohr calls it, they can be treated as particles in orbits under an inverse square law using ordinary Newtonian mechanics. Okay, so having established these rules that allow atoms to be stable, let's try and make contact with emission and absorption spectra and see if we can get some experimental evidence that Bohr's model is correct. Well, before Bohr's model of the atom, we thought that the frequencies of these emission lines from these spectra were actually the frequencies at which the electrons in the atoms either circled or vibrated, so that this was purely classical emission of electromagnetic radiation by an accelerating charge. Okay, so the observed frequency should match the orbital frequency of the electron, according to classical theory. But Bohr's model of the atom says no. The frequency of the emitted light is not related to the orbital frequency, but it is related to the difference in energy between the two orbits the electron is transitioning between. So the frequency has to do with not just a single orbit, but with the difference in energy between two orbits. Right, so if the orbit of the electron in the upper orbit has an energy E2, and the energy of the electron in the lower orbit is E1, then E2 minus E1, the difference in energy between these two orbits, is equal to Planck's constant times the frequency of light emitted. Okay, with that in place, we actually have immediately a quite natural explanation for discrete emission or absorption spectra. Emission spectra occur when electrons jump from a higher orbit to a lower orbit. If we label the orbits with integers, so n equal to 1 is the lowest orbit closest to the nucleus, followed by n equal to 2, n equal to 3, and so on, then for example we get the Lyman series of emission lines when the electron jumps between the second orbit and the first, the third orbit and the first, the fourth orbit and the first, and so on. Then we get the Balmer series when the electron jumps between the third orbit and the second, the fourth orbit and the second, the fifth orbit and the second, and so on. Paschen series, we're jumping between the fourth orbit and the third, the fifth orbit and the third, and so on. So each series is defined by the orbit the electron ends up in. Now, this is quite nice, and we'll show that it is quantitatively correct in a minute. But firstly, just to draw your attention to two questions that are raised in Bohr's model of the atom when you think about it carefully. Those questions are, how does the electron move between these two stationary states, these two orbits? What does the electron do to get from one orbit to the other? Bohr says it happens instantaneously, which seems quite alarming and certainly violates the idea that nothing travels faster than the speed of light. Also, and this is quite troubling, how does the electron know when to jump and which level to jump down to? Right? Why, when an electron jumps from the fourth orbit to the second, how does it know when to jump, and how does it know to jump to the second and not the first or the third? In Bohr's model of the atom, these questions are unexplained, and we're going to have to hope that as we develop this theory further and it becomes a more mature scientific theory, that we can bring in explanations for these things. If we can't, then we may have to go back to the drawing board and come up with something else that does work. The physicists of the time are acutely aware that they're having to drastically change established physical laws in order to make the behavior of atoms work with what is experimentally observed. In Bohr's 1913 paper, he says that the assumption, referring to his principles, is in contrast to the ordinary ideas of electrodynamics, but appears to be necessary in order to account for the experimental facts. So Bohr is saying, yeah, I know that I'm having to violate physical laws here, but I'm left with no option, right? The experiment is driving me to do this. And other physicists are quite understanding of this fact. Everyone is acutely aware that experiment is driving us to consider alternatives to established physical theories. Ernest Rutherford said in 1914 that Niels Bohr has faced the difficulties of atomic structure by bringing in the idea of the quantum. At all events, there is something going on which is inexplicable by the older mechanics. So he's saying that classical physics cannot explain the data that experiment is throwing up. And he's acknowledging that Niels Bohr is having to come in, bring in these new ideas, these quantum ideas. So let's make this a little bit more quantitative. Bohr's new principles that underlie his model of the atom say that the difference in energy between the upper orbit that the electron starts in and the lower orbit that it jumps down into is equal to h nu, according to Planck's formula. So nu is the frequency of light, that's equal to the speed of light, c, divided by the wavelength, lambda. So we can write the formula like this. Now, we want to make contact with Rydberg's empirical formula for the wavelengths of emission lines in discrete emission spectra, which, remember, for an atom of hydrogen, where the atomic number Z is equal to 1, the formula is 1 over lambda is equal to Rydberg's constant R times 1 over m squared minus 1 over n squared, where m and n are integers. Well, 1 over lambda, according to this first formula up here, is just equal to the difference in the energy between the two orbits divided by Planck's constant times the speed of light. Right, so this second equality here is predicted by Bohr's atomic model. And we can rewrite this by noticing, well, these integers that we just had to bring in from nowhere to describe the experimental data, they have this natural explanation now within Bohr's model. N, this integer here, the larger integer, is just the number of the orbit that the electron starts in, and m is the orbit that the electron ends up in. So we can replace the labels upper and lower on the energies here with n and m here. And let's call the difference in the energies between the two orbits delta E. Rearranging this a little, we get the formula that the difference in energy between the upper and lower orbits is equal to Planck's constant times the speed of light times Rydberg's constant, so all three of these are constants of nature, times 1 over m squared minus 1 over n squared. Okay, so this allows us to link Rydberg's formula with the actual physical picture of the atom and identify that these integers are just the numbers corresponding to the orbits the electron starts out in and ends up in. Or we can go a little bit further, because remember Bohr said that these circular orbits should be describable by Newtonian mechanics. It's just the transitions between the orbits that cannot be described by ordinary mechanics. Well, in the further reading that you'll do this week, we derive the following formula from classical mechanics, that this difference in energy between two orbits is just equal to a constant k squared times e to the 4 times m divided by 2 times 1 over L lower squared minus 1 over L upper squared. Now, K is just the electrostatic constant, 1 over 4 pi epsilon 0. Epsilon 0 is the permittivity of free space. This is the constant that appears in Coulomb's law, inverse square law of the force between two electric charges. So this is a constant of nature. E to the 4, well, E is just the charge on the electron. So that's a constant of nature. M is the mass of the electron. That's a constant of nature. What is L? Well, L is the angular momentum of the orbit. So L lower is the angular momentum of the lower orbit. L upper is the angular momentum of the upper orbit of the electron. So this comes from very simple circular motion, which is derived in the supplemental reading that you'll do. So in order for Bohr's model to work, this has to match this empirical formula that we just derived. Okay, so we have to ask, do these two match? And the answer is yes, if, firstly, the bottom here, if Rydberg's constant is equal to this collection of constants of nature. Well, to test this, all we have to do is plug in the known values of K, E, M, C, and H. And if you do that, you find that indeed this combination of those universal constants does end up equaling Rydberg's constant. So that's great. That's the first test of Bohr's model passed. It passes experimental test number 1. It also only works if the angular momentum, L, of the orbit is equal to an integer n times Planck's constant over 2 pi. So this says that the angular momentum of the orbit of the electron can only assume certain discrete quantities, right? It can be equal to 1 times h over 2 pi or 2 times h over 2 pi, but it can never be equal to 1.5 times h over 2 pi or 2.3756 times h over 2 pi. By the way, this factor h divided by 2 pi appears very, very often in quantum theory, and so it's given its own special name, h bar. So it's h with a bar across the top, the stem of the h. When you say it out loud, you literally call it h bar. So this is interesting because it tells us that angular momentum of the orbital angular momentum of electrons is quantized. It can only assume certain discrete values. It can't assume a continuous range of values. This is the second quantity that we've seen quantized after the energy of photons, which Planck and Einstein showed could only assume certain discrete values. The integer here, n, is called the principal quantum number, and it takes values 1, 2, 3, and so on. So it labels the orbit that the electron is in. And this is our first example of a quantum number, a number that labels the value of a certain quantity that is quantized. Another prediction that Bohr's model makes that can be tested against experiment is a characteristic size of atoms. So if you combine Planck's constant with the other fundamental constants that appear in Bohr's model in a certain way, you can make a quantity called the Bohr radius, which has units of length. And if you calculate this, it has the value of about 5 times 10 to the minus 11 meters. This is the predicted size of an atom, or characteristic size of an atom. By the 1910s, we were able to estimate the characteristic size of atoms from experiment, and we find that it agrees well with the predicted size from Bohr's model. So this is a second victory for Bohr's model of the atom, another place where it agrees with experiment. Finally, Bohr introduced the correspondence principle, which is very important philosophically as well as practically for the theory. The basic idea is that when we have to come up with a new theory of physics or science in general, that new theory can't overturn everything that has already been known. Right? Previous theories aren't necessarily going to be thrown in the trash can because they work. They have been shown to work. They have become theories because they have worked for a long period of time and describe many different phenomena really well. We can use Newtonian mechanics and Newton's theory of gravity to put probes on Mars, so they clearly work. We can use Maxwell's electromagnetism to generate, transmit, and pick up radio waves, for example. It clearly works. So whatever theory we're constructing here is not a replacement to these older theories. It is an extension of the older theories into a new domain. And in this case, what we're doing is we are extending our theories and changing them so that they work in the microscopic domain of atoms and subatomic particles. In order to make sure, though, that we are extending the theories rather than replacing them, there's one important requirement that must be fulfilled, and that is that at sufficiently high quantum numbers, which means as one transitions from the microscopic back to the macroscopic, then our new theory should smoothly change into our old theory. Or to put another way, the things that our new theory predicts should smoothly become consistent with the things that our old theory predicts. So, for example, classical theory says that the frequency of light emitted by a charge in circular motion is equal to the orbital frequency of that charge. Quantum theory says that the frequency of light emitted should be proportional to the difference in energy between the orbits that the electron is jumping to and from. As these orbits become very large, i.e. as the quantum number n becomes very large, so the orbit goes from being microscopic to macroscopic, then the frequency you get by doing the calculation in quantum theory must become equal to the theory that you get from classical theory. And in the supplemental reading, you'll show a proof that this is actually the case for Bohr's model of the atom. So, to summarize, atoms have a tiny positively charged nucleus with electrons moving outside them. In order to make electron motion stable, Bohr postulated two things that go against classical electromagnetism. He postulated that electrons move in stable orbits without radiating away their energy, and that they transition instantaneously between orbits by emitting photons with single frequencies given by Planck's formula. The model correctly predicts the emission line wavelengths in hydrogen and hydrogen-like atoms, and it also predicts correctly the size of atoms. Moreover, the model matches Maxwell's theory if you go to very large electron orbits, or equivalently very large quantum numbers, as required by Bohr's correspondence principle. And the model predicts that the electron orbital angular momentum is quantized. And that is the second thing that we have seen that is quantized after the energy of light that Einstein and Planck quantized.